Hello everyone, I'm Siddiqa Safa. I'm a junior IT student studying at American University of Afghanistan. So this was a data structure classes project or assignment that was given by Professor Ali Rahman Shinwari. What I'm gonna do in this assignment is that I'm gonna explain or find the majority element by using Boyer-Moore majority vote algorithm. So what is the majority element? This is the first step that we have to know because that is the question or the problem that we're having here, and we want to find a solution or an algorithm for it. So the majority element is an element in an array of n size where it appears more than n over 2 times. What does it mean? That means that it appears more than the half of the size of the array. Like if we have an array of size, for example, 10, then the half of the size of the array is 5, right? But this majority element will appear in this array 6 times or more than 5 times. Here we have an example. So here we have an array A is equal to 2, 1, 3, 1, 1, 4, 1. And here the size of the array is 7, and 7 to the divided by 2 is 3.5. That means this is the half size of this array. And the occurrence of 1 is 4. That means the size of, or the number of times that 1 appeared in here is 4. This means that 1 is the majority element in here. And we have another array which equals to 1, 1, 2, 3, 6, 5. This array doesn't have any majority element because the size of the array is 6, but there isn't any element that occurs more than half of the size of this array. Now, an element is not a majority element if it appears exactly n over 2 times. It means like if we have an array of size 10 and we have an element that appears 5 times, then that element is not the majority element, although it appears half the size of this array, but still it's not counted as majority element. It should be more than the half of the size of the array that we are having. Now, what is the algorithm that we are here presenting for this problem to solve or to find this majority element? Well, there are many ways to find this, the majority element in an array, like the brute force approach, using two nested loops or using sorting or hash table or bit manipulation algorithm. But we are using the Boyer majority vote algorithm, and there is a reason for it that we are choosing based on the efficiency of that algorithm. We will talk about the efficiency of algorithms later. So what is Boyer-Moore algorithm? The Boyer-Moore algorithm is an algorithm for finding the majority of a sequence of elements by using linear time and constant space. This algorithm was published in 1981 by Robert S. Boyer and J. Strother Moore. This algorithm finds the elements in an array that appears in an array more than half of the elements of the input. If there is one element like that exists in this array, then it returns that element as the majority element in here. But if there is none element like that in the array, then it will return that there is no majority element in this array. So let's see how it works. In Boyer-Moore algorithm, we have two major steps to follow. The first one is to find the candidate. Could be or could not be the majority element. Well, that depends on the next step. We will find that in the next step if it's the majority element or not. But now let's focus on this step. So it follows the following steps. First thing that it does is it loops through each element and maintains a count of majority element and the majority index and majority element index. If the next element is same, then increment the count. If next element is not the same, then decrement the count. If the count reaches 0, then changes the majority element index to the current element and set count again to 1. So here is the next step, the second loop that we will have. This loop is to check if the candidate that we selected for and in the first loop, is it the majority element or not. It will traverse through the element again and check each element that exists on the array and check if the count of the element that's found is greater than half of the size of the array or not. If it is, then it will be the majority element. But if it's not, then the candidate element is not the majority element, and it will turn no majority element exists. Here is the graphical representation of this algorithm. For the graphical representation, we represent an array here. We give an example of the array. This is actually the worst case of this algorithm that it can have. So the array has 1, 1, 1, 4, 6 as elements. We start from the first index, which is the index equals to 0 here, the first element, it equals to 1, right? Now the majority element is equal to the first index here, which is 1 for sure, and the count is equal to 1. Now we will go to the second one. So in the second one, the element is 1. It's the index is also 1 here, because it's the second index. And now we see that the majority element was 1, right? It is 1. So we check if the majority element equals to the element. If they are equal, then we will increment the number of count by 1. So count equals to 2. Now we will go to the third element of this array, which is 1. Now the majority element was also 1, is 1. So they are equal. That's why we increment the number of count by 3 again, by 1, which equals to 3. Now we will go to the next element, which is 4 in here, and the index is 3, the element is 4, the majority element is 1. Now we will compare it. We see that they are not equal. The majority element is 1, and here it is 4, the current element. So we will decrement the number of count. It decrements it by 1, so the number of counts now is 2. Now we will go to the last element, which is 6, or the index 4 of this array. And now we see the majority element is 1. They are not equal, so we will decrement it once again, and the number of counts equals to 1 now. Now, this was the first loop. Now let's go to the second loop. We found the majority element here, or the candidate element, and the candidate element here is 1 because the count is also 1. If the count was 0, then we would change it with the last element or the current element. That happens when we have an example of an array where there is no majority element, or none of them are equal. I mean, the majority element is equal to the current element, so we will reach the end of the array, and then we see that there is no majority element found, so we change the current element as the majority element, or the last element. But now we have the 1 as majority element, so we'll go to the second loop. So we will go to the second loop. In the second loop, we will check if the candidate element is the majority element or not. And we said that it is the majority element if it appears more than the half of the size of the array. Now let's check it out. So we will start by the first one, the first element in this array, which is 1, right? We see if they are equal, then the count equals to 1. We will increment count by 1. So yeah, they are equal. The candidate number is element is 1, and now the first element is also 1, so we increment the count by 1. Now we will go to the second one. The second one is 1, and it equals to the candidate, which is 1. So the count becomes 2. We just write candidate here because it's constant and it's gonna be 1 till the end. So yeah. Now we will go to the third element of this array. The third element of this array is 1, and now we see that it is equal to the candidate element that we have. The candidate is 1, 2, so the count number equals to 3. Now we will go to the other element of this array, which is 4. We see that 4 is not equal to candidate, so we won't do anything here. We will just go with the 3. The count will not decrement or increment, or anything will happen to the count. The count remains as it was, so it's 3. And now we will go to the last element of this array, which is 6. And 6 is not equal to the 1, so the count still remains the same, which is 3. Now we found the candidate. Now we found that the count number is 3, which is greater than half of the size of the array. The array has 5 elements. The half of the size of the array is 2.5. And the count that we found here is 3, which shows that it's the more than half of the size of the elements. So the candidate number that we had, or we found on the last or previous, or this part of the algorithm, the first loop, is the majority element. And in the second loop, we found that it is the majority element. Okay, so now let's go to the complexity analysis of this algorithm. But before starting the complexity analysis, there are some things that we have to know about the complexity analysis of algorithms. Well, we mentioned before that we chose the majority, the Boyer-Moore algorithm, because of the efficiency that it has. Efficiency of algorithm is mainly defined by 2 factors. One is the space, and the other one is the time complexity or analysis of the algorithms. So let's know how to find the complexity or space complexity or time complexity of algorithms. So the space complexity means that it's about the space that's required for the algorithm, and the time complexity is the time that's required for an algorithm to complete its tasks um, with respect to the given input. The asymptotic notation is used to analyze the complexity of the algorithm, and based on that we can find the most efficient algorithm. For asymptotic notation we have three notation. We have omega notation, we have big O notation, and we have theta notation. Big O notation defines the upper bound of an algorithm. That means it sees the maximum time that's taken by an algorithm in order to give a result, or we can say the worst case of the algorithm. And the Bake notation is the mostly used notation among all other notations. So let's go to the time and complexity of the Boyer-Moore algorithm. So in here we have two traversals of the array to perform the constant number of operations per input time. So the time complexity of this array is big O n. In other words, it's the linear. We call it linear time complexity of the algorithm. This means that the time will increase linearly with the size of the input. If we increase the size of the input, that will increase the time complexity as much as we increase the size of the input. So it's always linear. And linear time complexity is one of the best complexity situations that an array can have. And that's why, because it makes an array more, an algorithm more efficient. And that's why we are using this Boyer-Moore algorithm for solving this question. The space complexity of the Boyer-Moore algorithm is big O1. That means there is no extra space required. That means that the space complexity is always the space that's taken, or the memory, the amount of memory taken or needed by this algorithm is always constant. It won't be affected by the input that we will give to it. Like if we increase the number of inputs, it won't affect the space complexity. It will always remain constant. In random access model of computing usually used by the analysis of algorithm, each of these values can be stored in machine word, and the total space needed is 0, 1. So for this algorithm, we just need the space for one element and one counter. That's why it's always the same. And the other parts of it is going to be saved in the random access model of computing. Overall, the space complexity is constant, and the time complexity changes according to the input that's given. Here is the graph to show it better. If we increase the time, as much the time, the input of an element, then an array, then the time will increase that much. For example, if we have 10 elements in an array and the time is 0.02, the time it takes, then if we give it 20 elements, then the time will be 0.04. It will increase in a linear way, linearly. And for the space, it will always remain the same. For example, if the space memory that's taken is 1.8 megabytes, then if we increase the number of elements in an array, the space will still be the same, the constant. Now I'm going to show you the code. This is the first function that we are having. It checks or finds the candidate. So it takes an integer array and then integer size. What it does, the first thing is that we declare a majority element index, and we define it 0, and then we declare count and then define it as 1. Now we go to the first loop of it. We'll iterate until it reaches the size of the array, and then we give it the condition for each iteration. And if the count number equals to 0, let's say we reach the last element of the array and we don't have any candidate element and the count is 0. So what it will do, it will change the majority element index to I, or to current index, and then the count number will be 1. So we will have a Boolean function here that will return true or false, or 0 or 1. And then we will start a loop. The loop will iterate until it reaches the size of the array, or the last element of the array. And then what it does, for each iteration, it will check if the current element is equal to the candidate. If it equals, then the count will be increased by 1. Or we will increment it. We will see if the count is greater than the size over 2. Size of the array over 2, which is the half of the size of the array. If the count is greater than that, then return 1. That means return true. That means that this is the majority element. Else return 0 or false. Then we're gonna print it. We're gonna print it by, first of all, the first thing we do is we declare a candidate here, and then we give the candidate find candidate function here for it. So this function will find the candidate, and then it will assign it to this cand. And then we will check if the function is majority element. If it's true, if it brings true or 1, then it will see out the candidate, and then we'll say that this is the majority element. Else it will say or it will print that no majority element exists in the array. In this function is majority, we just checked if it is the element or not, and it would return 1 or 0 because it was Boolean. And after that we have our main. In our main we're gonna call the function. So first of all we're gonna declare an array that we want to give it, and we want to see if it has a majority element or not, and then we declare the size of it. Now we're gonna print the majority element. In the print function we saw that if the majority element brings true, then it will print it. Otherwise it will print that no majority element exists. So let's just run this program. 1 is the majority element here because the size of the element, the array is 5, but 1 is the size of 1, or the occurrence of 1 is more than the size of this half of the size of the array. So this is the code for the Boyer-Moore majority vote algorithm.